This is an example of base catalyzed hydration of aldehydes and ketones. Since in this reaction, water is not used and sodium hydroxide is used as a direct source of hydroxide ion, then hydroxide ion is a strong nucleophile and is basic, very strong basic species. So therefore, it can easily attack the carbon in here, and to get this, this ion in here again, you have a basic oxygen there, and it's going to grab a proton from water because you are using aqueous sodium hydroxide or potassium hydroxide solution. Then you get your diol this way. And so there are two ways you can make diol, geminal diols from aldehydes and ketones, either in acidic medium or basic medium. In this slide, we are looking at how to make cyanohydrin using aldehydes and ketones. And, the type of reaction that takes place in here is base catalyzed reaction. The reason is because cyanide is very strong nucleophile, and since it's a strong nucleophile, it's going to attack that carbon right there. And you're going to get this intermediate. Again, when you look at the intermediate, you see oxygen with lone pairs and a negative charge. And we know, again, it's a basic oxygen. And it's going to grab a proton from this compound in here. And in order to make these reactions to go to completion successfully, we always pair up the conjugate acid-base pair. That's why you have this acid in here in the solution with this base. And like I mentioned, this is a base catalyzed nucleophilic addition reaction. And in this reaction, you're going to get the cyanohydrin. And you're going to see the same compound again in another chapter, how to use this to make carboxylic acid. And this is mentioned on page 906 of your textbook, that the acid catalyzed reaction of cyanohydrin would change the cyanohydrin to carboxylic acid. As it was mentioned before, the aldehydes, they do all kind of nucleophilic addition reactions better than ketones. Like in here, you can look at you can look at this reaction, and it goes to 100% completion. So there is no equilibrium issue in here. But when you start doing the same reactions with ketones, you'll see that the smaller the ketone is, you get more product compared to when you have a larger ketone. And in here, since you have such a bulky groups in here, look at the amount of product that you get, and look at the equilibrium position is shifting toward the reactant. Here is a reaction between ketones and aldehydes with compounds containing nitrogen and at least 2 hydrogens on the nitrogen. So the reagents that you can put in here could be ammonia, could be primary amine, or could be any other type of nitrogen containing compound, as long as the nitrogen has 2 hydrogens on it. And these kind of reactions are called condensation reactions also. The reason is because when you look at the product, one of the product is water. So in order to get the water as one of the products, you need to have 2 hydrogens and an oxygen from this side. So the oxygen is going to come off from carbon in here, from a carbonyl compound, and 2 hydrogens are coming off from the nitrogen containing compound. That's why I said the substance that you use as your source of nitrogen, that nitrogen or one of the nitrogens in the compound has to have at least 2 hydrogens, so you can get the water molecule. And when you do this type of reactions, these type of reactions are supposed to be done in basic medium, and they are very pH sensitive, and the pH should be around 4.5. So when you look at the product, we saw this product before in other slides, where we used Grignard reagent and treated Grignard reagent with the carbonyl compound, and we formed imine. And that's another way to make imines. Okay, imines are the compounds that carbon and nitrogen are doubly bonded. and amines in general are known as Schiff bases. Here is a mechanism of how to form an amine, and as you know, ammonia or amines are weak nucleophile, and in order for the reaction to happen, we need to acidify the solution. That's why this proton is there to form with the form a bond with the oxygen. And when the bond is formed, then it means the nucleophile can attack that carbon. And when the attack is made, we get this intermediate in here. And when the intermediate is formed, again, we have extra hydrogen from, that needs to be removed from nitrogen. And we can use any base that we have in the solution to remove that proton. And when the proton is removed, we get this hemi-aminol compound. Okay. And now, if you want, you can stop the reaction in here and not to continue, but then, the reaction can continue. And then, again, it's in a basic medium. Oxygen is going to get protonated, and this is going to leave as a living group. Water can be, can act as a living group and then leave. And then when the water is left, that's how you get the double bond formed between nitrogen and carbon, and then you get your amine. Here are some examples of the reactions of ketones and aldehydes with nitrogen-containing compounds. And when you look at all these nitrogen-containing compounds, like I mentioned before in another slide, all the nitrogen-containing compounds, they need to have two hydrogens attached to your nitrogen. And what is going to happen to put the products together? Simply you remove two hydrogens from your nitrogen-containing compound, and you remove the oxygen from your aldehydes or ketones. Then you form a double bond between the carbon of your aldehydes and ketones and the nitrogen that is left from your nitrogen-containing compound. So that's when you look at all these three examples, that's what you will see. And one of the product is always the water. Like I mentioned, these are called condensation reactions. Here are more reactions of aldehydes and ketones with different type of nitrogen-containing compounds. And when you look at all these compounds, what they have in common, they have a nitrogen that nitrogen has two hydrogens. So then you're going to get a reaction between the nitrogen that has two hydrogens with the carbon there. Like I said, you remove the oxygen, you remove the two hydrogens, then you form a double bond between carbon and nitrogen. Then you're going to get the compounds that are shown in here. So when you look at all these compounds, that's basically what happened, that the nitrogen that is forming the double bond with the carbon lost two hydrogens, and the carbon lost the oxygen. In here, you are learning about the formation of acetals. If you have learned the formation of, geminal diol in previous slide, then you already know formation of acetal. Because for hydration, we use the water molecule. For formation of acetal, we are using alcohol. So basically, this is again acid catalyzed reaction because we are using alcohol, and alcohol is a weak nucleophile. And that's why these reactions are done in acidic medium. And when the reaction is completed, you add 2 moles of acid, alkyl oxide ion on the carbon. And this type of compounds are known in general as acetal because we are using aldehyde. If you do the same reaction with the ketone and you are using alcohol to react with the ketone in acidic medium, you're going to get the acetal, but this type of acetal are known as ketol because you are using a ketone, but principally they are the same. And when you look at this type of reactions, you will see that you are adding 2 OR group on the carbon that is coming from aldehyde or ketone. And for this, you need to use 2 moles of alcohol to go all the way to acetal or ketone, because if you are using only 1 mole of alcohol, you are going to get what is known as hemiacetal. And again, this type of reactions, they have equilibrium issues, as you can see in here. So the reaction can go back and forth because there is an equilibrium between the reactant and the product. Here is the mechanism how to form hemiacetal, meaning we are only adding one alkoxy group on the carbon. So again, as I mentioned previously, these reactions are supposed to be done in acidic medium, so you need an acid, and you have an acid in here, and then the oxygen is going to grab a proton and get protonated, and it's going to form this protonated ketone, and then this can stay in 2 different resonance forms, and this is the form that we're going to use for the mechanism. And basically what it is, since you have a positive charge on the carbon, it means this carbon is electropositive, then the alcohol is going to act like nucleophile and attack that carbon there. And when the attack is made, then we're going to get this species right here. But we know this is going to act like water now. It's going to, it's going to become a good source to get, the good source for getting rid of a hydrogen there. So all you going to need is another base that is going to come and take this proton off. When the proton is taken off, then the pair is going to shift on the oxygen, and then we get an alkoxy group added to the carbon there. So in the previous slide, we learned how to make hemiacetal. Now, if you want to continue the reaction, again, you can add more acid to the mixture. And when you add more acid to the mixture, then this oxygen is going to get protonated because this one was already added. And then when we have oxygen being protonated, we're going to get the water molecule that can leave. And when it leaves, it gives us this intermediate in here. And they both are 2 different resonance forms for the same, intermediate. And when this intermediate is formed, now you have a positive charge there in this form of this intermediate. Then the alcohol can attack the carbon right there. And when the carbon is attacked, we're going to get this species right in here. Then again, we need to remove that proton, and to remove the proton, we can use the base. In this case, is the alcohol that we are using you're using to do the reaction, and we get what is known as acetal. So we can go from aldehydes and ketones to hemiacetal, then from hemiacetal to what is known as acetal, or if you use ketone to ketol. As we learned that, in the previous slides, when we have hemiacetal or acetal, we have an equilibrium between the reactants and the products. So we can easily reverse the reaction like it is shown in here. So if you have acetal or hemiacetal and you want to reverse the reaction, all you need to do is to, add more acid to the mixture. And like it says in here, excess of water can also push the equilibrium toward your ketone or aldehyde. Here we are learning how to make cyclic acetal. So to make cyclic acetal, you would make it exactly the same way you did before, but the only difference is you need to use a diol, right? And in this example, we are using ethylene glycol. So basically what is going to happen, like I said, this is a condensation reaction. You are going to get a product, water as a product. Then to get the water as a product, in here, these 2 hydrogens from your glycol are going to be taken away, and oxygen from your carbonyl compound is going to be taken away. And then you are going to get a cyclic acetal. This is an important reaction because you can use this technique to protect your carbonyl groups in other reactions if you don't want your carbonyl group to react with what you add to the mixture. So simply what you do first, you add ethylene glycol to the